Okay, so today we're going to go ahead and go over notes number 3, mass to mass, and other unit conversions. So if you guys remember that we did go over moles last semester and a few days ago. So our mole map is now going to double in size. Okay, so it's no longer just one side of our mole map, it's doubled. Okay, so how do we use our mole map? Well, you're still using it the same way. Okay, your starting point is always going to be on the given side. So basically it's going to be this side of your mole map. Okay, your end point, or what you're trying to find, is going to be on the right side of the mole map. Okay, so it's the same thing as far as you're starting from what's been given in the problem or the equation. So you're going to start here, and then whatever you're looking for or whatever your question is asking for should be one of these four on the right side of our mole map. Okay, so once you've reached your destination, then you're going to go ahead and mathematically solve it by multiplying all your values on top, multiplying all the values on the bottom, and then you're going to divide those two values. Okay, so there are a few notes that you should know before you actually start balancing, or I'm sorry, once you actually start calculating, is that you have to make sure that you have a balanced chemical equation. Okay, because remember, our notes from yesterday was actually this part right here, converting from mole to mole. That's our coefficient ratio from our balanced equation. Well, remember, we need a balanced equation to convert from moles of one substance to moles of another. Okay, and then that really is the only note. Okay, make sure you have a balanced chemical equation, so that way when you're converting, you don't have an issue once you get to that conversion factor there. Okay, so mass to mass conversion calculations. So you have nitrogen plus 3 hydrogen atoms yields 2 ammonia atoms. So just like yesterday, in order to go from the mass of one substance to the mass of a new substance, a mole-to-mole conversion will be necessary. Okay, so let's go ahead and take a look at this example right here. So it's saying, calculate the number of grams of NH3 produced by the reaction of 5.40 grams of hydrogen with an excess of nitrogen. Okay, so your given is going to be 5.40 grams of hydrogen. And what we're trying to find is grams of NH3. So if we take a look at our mole map, well, our given, I like to divide this up. So that way I know that this side is for my given, and then this side is for my wanted, or whatever I'm trying to find. Okay, so if this is my given, 5.4 grams of H2, then that would mean this right here is going to be my starting point. I am starting at mass. Okay, my question is asking for calculate the number of grams of ammonia. So grams of ammonia would be on this side of my mole map. Okay, so if I'm looking at my mole map, remember you have to stay on the road of your mole map. So to get from mass of my given, which is H2, right? I'm trying to get to mass of ammonia. So that means I have 1, 2, 3 conversion factors for this one problem. Okay, so again, that was 3 conversion problems. So my given is 5.40 grams of H2. And again, I said we have 3 conversion factors for this one problem. Okay, so my first conversion factor is going to be, taking a look at our mole map, we're going from mole mass to mole. That's our first conversion, which is molar mass equals 1 mole. Okay, so if my given was grams of hydrogen, then on the bottom we know it also has to be grams of hydrogen, because remember, these have to cancel out later on. So then my 1 mole is going to be on top. So how do I know what the molar mass is for hydrogen? Well, we have to look at our periodic table. Okay, so hydrogen, taking a look at our periodic table. Okay, you guys should actually already know this part by now as well. Okay, just finding the molar mass. So hydrogen has the atomic mass of 1.008, and we have 2 hydrogens. So 1.008 times 2 is 2.016. So my molar mass is 2.016 grams for hydrogen. Okay, so now my second conversion factor, right? We went from mass to moles, and we have that conversion factor down. Our next conversion factor would be our coefficient ratio from our balanced equation. Okay, so when we put our, I don't think we need our periodic table anymore, so let me just zoom in again. Okay, so when we put in our conversion factor, how do you know which one goes to which? Remember, it's always going to be mole to mole conversion. That's what the coefficient ratio is. So if this is moles of H2, then diagonal of that also needs to be H2. And then moles of whatever I'm trying to find is going to be on top. So moles of NH3. Okay, so we have to look at our balanced equation to determine what our coefficients are. So our coefficient for hydrogen, our balanced equation is up here. So our coefficient for hydrogen would be A3. And our coefficient for ammonia is A2. Okay, so now that's our second conversion factor. Now our last conversion factor, okay, this is our first, this is our second. Now we're back to molar mass equals 1 mole of our wanted. Okay, so remember our diagonal rule. If this is moles of ammonia, then diagonal of that needs to be moles of ammonia. Okay, and then remember our conversion factor was for 1 mole. It's going to equal the molar mass of NH3. So again, we have to determine what our molar mass is for ammonia. Nitrogen is 14.007. Okay, hydrogen is 1.008 times 3. So 14.007 and 3.024. So that is 7 plus 4, that's 11. 3, 0, 7, and 1. Okay, quick mental math. So our total is 17.031 grams of ammonia. That's our molar mass. Okay, so to solve, okay, well, before we solve, we have to cancel out our units. Grams of hydrogen is going to cancel out with grams of hydrogen. Moles of hydrogen is going to cancel out with moles of hydrogen. Moles of ammonia cancels out moles of ammonia. So the only unit we have left is going to be grams of ammonia. So that would mean we would have to multiply everything on top. Okay, so I'm just going to use my basic calculator for this since we don't have any scientific notation. Okay, so we have 5.4, and I'm going to do all the numbers on top. Okay, so that's 5.4 times 2 times 17.03. So times 2 times 17.031. Okay, and we get 183.9348. Okay, then all my numbers on the bottom, we have 2.016 times 3. Okay, so that's 6.048. Okay, so divide those two numbers, 183.9348 divided by 6.048. Then you get 30 and then 0.4. I'm just going to stop right there because my significant figures, I have 3 significant figures, so my final answer should also have 3 significant figures. Okay, and then our unit is going to be grams of ammonia, so grams of NH3. Okay. All right, so another way of calculating, I actually like to do it one at a time, and I go in kind of a zigzag pattern. Okay, so it's always going to be 5.4 times 1 divided by 2.016. Okay, then I push enter, then times that by 2, okay, then divide by 3. Then I'm going to multiply by 17.031, then divide by 1. But since it's just a 1, I don't necessarily have to divide. Okay, so I'm going to show you why that works. So let's go ahead and try 5.4. And then, okay, so 5.4 divided by 2.016, and push enter. Our next step is going to be to multiply by 2. So multiply that by 2, enter, divide by 3, enter, then multiply by 17.031, enter. So if you notice, I still get the same answer, 30.4125. Okay, I just did it one at a time. Okay, so there's a number of ways you can do it. As long as you're doing it correctly and end up with the same answer, then there shouldn't be any problem. Okay, so you can either multiply all of them on top, multiply all of them on bottom, then divide those two numbers, and you should get an answer. Or you can do it the way I did it. You just did it one at a time. 5.4 divided by this, multiply by 2, then again divide by 3, then multiply by 17.031. Okay, so you can do it either way. You should still end up with the same answer. Okay, so let's go ahead and work on some practice problems then. Okay, so if you still don't understand what we're doing, let's go ahead and take a look. So number 1, how many grams of oxygen are produced when a sample of 29.2 grams of water decomposes? Well, first off, I need a balanced equation. I was not given one, so I'm going to need to make my own. Okay, so the equation that I'm getting from this is water decomposes. Okay, and it's saying how many grams of O2 are produced. So I know that oxygen is going to be a product when water decomposes. So water is H2O, and then if you guys remember what decomposes mean, decomposes means that we are breaking apart. So the only way to break that apart is to separate hydrogen and oxygen. Okay, remember that hydrogen is a diatomic, oxygen is a diatomic, and when they are alone, they need that subscript. Okay, so now we need to balance our equation. Okay, so hydrogen, I have 2 on my reactant side and 2 on my product side, so hydrogen is balanced. But oxygen, I only have 1 on my reactant side and 2 on my product. So since oxygen is not balanced, that means I'm going to have to multiply my reactant side by 2. So I'm going to put a 2 right there. Okay, so because I put a 2 there, that's going to change the number of hydrogens I have to 4 hydrogens. So that would mean on my product side, I'm going to have to multiply this side by 2 also. Okay, so I now have a balanced chemical equation. Okay, so I'm just going to erase this for the sake of space. Okay, so now that we have a balanced chemical equation, we can go ahead and try to solve our problem. Okay, so remember we were given 29.2 grams of water, so that would mean, I actually have a different mole map than you guys. Okay, but that would mean if we were, let's see, maybe I can squeeze it in. Okay, so if we were given grams of water, that means on my known side or my given side, I'm going to be starting here at mass. And I've been asked to look for grams of oxygen. So if it's grams of oxygen I'm trying to find, then I would end up here. So that would mean I have 1, 2, 3 conversion factors that I would have to use. Okay, 1, 2, and 3. All right, so let's go ahead and set up our equation. Okay, so again, that was 29.2 grams of water is going to be our given, and we're going to multiply that by our first conversion factor. Our first conversion factor is 1 mole equals molar mass. So if this is grams of water, then I know at the bottom is going to be grams of water as well. And on top is going to be my 1 mole of H2O, right? Because my substance that I know is H2O, and I'm trying to find substance B, which is oxygen. Okay, so I have to calculate my molar mass for water. So again, hydrogen is 1.008 times 2. That's going to be 2.016. And then oxygen is 15.999, and we only have 1. So 15.999 times, or I'm sorry. Let's just push enter. 15.999 plus 2.016, and we get 18.015. Okay, that's our molar mass for water. Okay, our second conversion factor now is going to be right here. We're going to be converting from mole to mole. Okay, so if this is moles of H2O, then on the bottom needs to be moles of H2O as well. And then what's on top is going to be moles of my unknown substance, which is O2. So moles of O2. Now we have to go back to our balanced chemical equation to find out what our coefficients are. So our coefficient for water is 2. Okay, and our coefficient for O2 is a 1. Okay, and lastly, our third conversion factor is going to be 1 mole equals molar mass. Okay, so if this is moles of O2, then on bottom should be moles of O2 also. And then what we're trying to find, which is grams of O2, goes on top. So oxygen, 15.999 times 2, that's 31.998 grams. Okay, and then we can go ahead and cancel out our units. Grams of water cancels out grams of water. Moles of water cancels out moles of water. Moles of O2 cancels out moles of O2. And we're left with grams of oxygen. Okay, so remember, I like to do my math one at a time. So it's going to be 29.2 divided by 18.015. Push enter. Then our next step is to again divide by 2 and then multiply by 31.998. Okay, and we get 25.9. Okay, so 3 significant figures. Answer is, oops, I don't know why I put it 3. Okay, 25.9, and the unit that we're left with is grams of oxygen, so grams of O2. Okay, so really quickly, I'm also going to go ahead and do number 2. Okay, so number 2, using the same equation, so this equation right here. Okay, how many liters of hydrogen gas are produced when 1.33 times 10 to the 17th power molecules of water decompose? So again, my given is 1.33 times 10 to the 17th molecules of H2O. So on my mole map, I am right here at particles. And my question is asking for liters of hydrogen. So that would mean I'm going from particles to mole to volume. So this is my first conversion, second conversion factor, and third conversion factor. Okay, so let's go ahead and try to use those and plug them into our problem. Okay, so my first conversion factor is 1 mole equals 6.02 times 10 to the 23rd. So if this is molecules of water, then at the bottom should also be molecules of water. So my 6.02 times 10 to the 23rd is going to go on the bottom. Molecules of H2O, and my 1 mole is going to go on top. Okay, next conversion factor, the second conversion factor is going to be from mole to mole. So what goes on bottom is going to be your mole of your known substance. On top is going to be the mole of your unknown substance. So, okay, mole of your known substance, which is H2O, and our coefficient for H2O is 2, and then the mole of our unknown substance, which is hydrogen. Okay, liters of hydrogen. Okay, and again, my coefficient for hydrogen is a 2. Okay, and we're going to multiply that by our last conversion factor. Our third conversion factor is 1 mole equals 22.4 liters. So if this is moles of hydrogen, then diagonal of that is also going to be moles of hydrogen. And then my 22.4 liters is going to go on top because that's what I'm looking for. I'm looking for liters of hydrogen. Okay, so when we cancel stuff out, let me zoom in. Can I zoom in? Okay, I guess it doesn't want to let me zoom in. Okay, but molecules of water is going to cancel out molecules of water. Moles of H2O is going to cancel out moles of H2O. And mole of H2 cancels out mole of H2. But before I actually start calculating, I can also cancel out 2 divided by 2 because 2 divided by 2 is just 1. Okay, so what I'm really left with is 1.33 times 10 to the 17th divided by 6.02 times 10 to the 23rd, then multiply that by 22.4. So, okay, I can't use a regular calculator for that, okay, because I have scientific notation. Okay, so on your calculator, okay, let's see if you guys can see this. Okay, I have 1.3, use parentheses, 1.33 times 10 to the 17th power. Okay, and we're dividing that by, use parentheses again, 6.02 times 10 to the 23rd power, and we get that crazy number. Okay, and then we're going to multiply that by 22.4, and we get 0.00005. Now, our given is just 3 significant figures. So how do we convert this to 3 significant figures? Remember, all your leading zeros are insignificant, so none of those count except for your 5. So what we do is we can go ahead and convert this to scientific notation. So 0.12345, then another 5. Well, to convert that to scientific notation, 5.00 times 10, okay, now I have 3 significant figures, right? So 1, 2, 3, 4, 5, 6. I've moved my decimal 6 times, okay, and because this is a tiny number, it's going to be -6. Okay, I've moved my decimal 6 times. Okay, so this would actually be my final answer, 5.00 times 10 to the -6 liters of H2. Okay, so if there was something that was unclear to you or you didn't understand where I got something from, please ask me questions. We do have a quiz on Thursday, and a majority of your quiz is just this. Okay, so if you don't know how to do this, you're going to be in trouble for that quiz. Okay, also you have some balancing in your quiz. So if you don't know how to balance, that might be a problem for you also. We're not saying that you have to write your own equation, but you do have to balance the equation that we give you. Okay, so again, if you have any questions, please don't be afraid to ask.